So good evening, everybody. My name is Talal Rajab. I'm the head of program for Tech UK's Cyber and National Security Programme. Quantum technology is a really exciting topic for an organisation like Tech UK and a major opportunity for the UK as a whole. Thanks to the competitive global position of our research base, which will hopefully continue post-Brexit, touch wood, and the willingness of UK companies to innovate and collaborate, the UK has a chance to be a world leader in a new and exciting £1 billion sector, which we predict as an organisation will only continue to grow. That is the reason why our government is investing 270 million, like Steve mentioned earlier, in quantum technologies, aiming to realise its potentially transformative impact across business, government, academia and society. And that's also the reason why government published a comprehensive national strategy for quantum technologies in 2015. However, for the layman, which I am definitely one of those, quantum technology sounds like science fiction, a theoretical possibility, but not a technical reality. This, however, cannot be further from the truth. The technology has the potential to transform the everyday lives of citizens, from how we communicate with each other, how we manage our own health and conduct financial transactions. And that is why I'm so excited, but slightly worried to be chairing the session today. After telling my CEO that I'll be here chairing today, he sort of nominated me as the expert within Tech UK for quantum and start doing a lot more work around quantum for the year. So thank you, Steve and SciNation, for that extra piece of work for myself. So as Shadi outlined earlier, we'll first take an overview of the landscape for quantum technology with presentations from some very exciting companies. We've got D-Wave Systems, QX Branch and Quantum Base. These companies will present for 5 minutes apiece and then we'll give you all an opportunity to ask them questions. We'll then move swiftly on to our expert panel discussion where we'll delve into the, I guess, what's the billion-dollar question, is the world ready for quantum? We have some esteemed guests in the form of Andrew Lloyd from BT, Professor Keith Martin from Royal Holloway University, Richard Murray from Innovate UK, Shadi Razak, who you heard from earlier from SciNation, and Kelly Richdale from ID Quarantine. So without further ado, let me introduce you to our first company who'll be presenting today, D-Wave Systems. D-Wave Systems is currently the world's only manufacturer and seller of commercial-grade quantum computers. So with 3 generations of field-deployed systems, top-tier customers including Google and NASA, unprecedented performance results, and the ability to offer access to machine via the cloud, the company is well positioned to bring quantum computing into the mainstream. So I'd first like to call up Dr. Colin Williams, Director of Strategy and Business Development, at D-Wave Systems. Thank you.
Me to this event. It's always great to come to London, and I know there's a lot of excitement around quantum. D-Wave Systems today is the only company out there selling a large-scale quantum processor of any kind, and we make our processors to be a sort of network or internet integrated from the get-go. So this was actually one of the things that we did from the very beginning. We made a full-scale processor, and from the very beginning, we made it available over a remote internet connection. So you can actually sit in London and program a D-Wave machine anywhere in the world and get results back. So people can access quantum computing resources much more easily than you might think. Our business model is basically to sell systems standalone. Some customers like to have the quantum computer local to them, but many more of our customers actually use our quantum computers in the cloud. So of all the people you hear as D-Wave customers, there's probably several times that many using the system remotely in the cloud. We're a very innovative company. We have an unusually large patent portfolio, which has been one of the main reasons I think we've been able to raise a significant amount of venture capital. And we're now very happy to see that there's an emerging software ecosystem of companies who are developing compiler tools and software development kits to write applications to our quantum computer design as well as those of other people as well, such as QX Branch, which is here tonight. And there's a few others. There's even one in the UK now called Cambridge Quantum Computing as well. One of the most gratifying things, actually, is to see people copying our approach. So for the longest time, D-Wave was pretty much the only company making an annealing-based quantum computer. But within the last year or so, both Google has started making what they call Annealer 2.0, and IARPA, which is the US intelligence agency's version of DARPA, they have a new program called Quantum Enhanced Optimization, which is also based on annealing. And we actually see this as a good sign, because when you go to venture capitalists looking for money, the first thing they ask is, if you're the only one doing this, it's a little suspect. So it's good to see other people doing the same thing. So this is what our product looks like today. This is the D-Wave 2X system. From the outside point of view, it looks like a very large black box, about 3 meters by 3 meters by 3 meters. Inside the large black box is a dilution refrigerator, which contains a quantum chip at the base of the refrigerator. And we have to cool that chip down to 10 millikelvin, which is about 180 times colder than interstellar space. And we have to shield it from all sorts of radio frequency, noise, and interference to get the quantum effects to sort of turn on. And we make all this available to people through a standard internet connection, so you don't need to know any quantum physics to use the D-Wave system. The chip itself looks remarkably like a regular chip. The only thing that's really exotic about it is it's made of an element called niobium, which becomes a superconductor at very low temperatures. It's why we have to cool it down. But we actually make this chip in a regular CMOS semiconductor foundry. In fact, the foundry makes chips for Intel as well. So we use state-of-the-art lithography capabilities to make these devices. The D-Wave system has been applied to many different fields already. So fields ranging from sort of mathematics and computer science to biosciences and healthcare. So although the chip is not a universal quantum computer, it's a very specialized kind of quantum computer, the kinds of things it can do can be applied in many, many different fields. And so we think this gives us access to a lot of very attractive markets. The most interesting market for us is actually in machine learning and AI, because what we are now beginning to see is that the chip natively solves one of the core problems which you need to train a large-scale deep learning system. And it does this very, very quickly and natively. So that's likely to be the sort of killer application that we look at going forward. One of the most interesting things about the D-Wave system is the amazing performance results that some people have reported. So Google was originally trying to answer the question of whether the D-Wave chip is actually performing quantum annealing or simulated annealing, which is a classical analog. And so they devised an experiment that if the chip was doing quantum annealing, it would end in one state, and if it was doing simulated annealing, it would end in another state. And they compared the running time of the D-Wave chip to solve that problem to simulated annealing, the best they could write, and also to quantum Monte Carlo. And they found that, for sure, the D-Wave chip was running quantum annealing, so it was a sort of proof of quantumness. But along the way, they discovered that the D-Wave chip was also incredibly fast compared to QMC and simulated annealing for this problem, about 100 million times faster. And they thought that was sufficiently newsworthy. They actually held a press conference in December of 2015 to report that. And just to get the classical data to compare against the D-Wave chip, Google spent $1 million of HPC computer time to get that data. Now, this particular problem is one that can be solved a lot quicker using different classical algorithms, but Google and D-Wave aren't particularly fazed by that because we know why those algorithms are fast for this problem, and we can change the future design of the chip to make it be far faster than anything we can do classically for a wide range of these kinds of optimization and sampling problems. So, thank you.
Just take a seat on the stage.